Hi, I am Raghavan, Chemistry Faculty from All Force College. I invite you all for the All Force Chemistry e-learning classes. Session 31. In this session, we are going to discuss about some revision concepts of Schrödinger wave equation, quantum numbers, and shapes of the orbitals. Okay, in the last session, we completed shapes of s orbital, p orbital, and d orbitals we have done. Okay. Now today in this session we are going to take up the revision concepts of Schrödinger wave equation, quantum numbers, and questions based on orbitals. Okay, that is revision concepts. Okay. Now in Schrödinger wave equation, what is the Schrödinger wave equation? What is the significance of Schrödinger wave equation? The Schrödinger wave equation is represented like this: dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square e minus v psi is equals to 0. That is Schrödinger wave equation. What is the significance of Schrödinger wave equation? It explains the probability of finding electron around the nucleus. Schrödinger wave equation signifies to explain the probability of finding electron around the nucleus. Yes. That means it explains the existence of orbital. The maximum probability of finding electron is orbital only. Okay, that means it explains or it gives the idea about orbitals. Then what is psi? Psi is the wave function. Okay, so since psi could not satisfy the boundary conditions, so psi has no physical significance. That we explained that. Okay, psi has no physical significance. What are the boundary conditions of psi? Which explains eigenvalues or eigenfunctions. So that is the boundary conditions of psi. 1. Psi must be finite, not infinite. Psi must be finite. Second condition, psi must be single digit. Third one, psi must be continuous. Psi must be continuous. That is from plus infinity to minus infinity. Okay. So these are the boundary conditions of psi. Since it could not explain, it could not obey the boundary conditions, psi has no physical significance. Therefore, introduced psi square. Psi square is introduced. What is that psi square? It is called probability function. It is called probability function. Okay. The psi square gives the complete idea about maximum probability, that is 95% probability of finding electron around the nucleus, that is called orbital. Okay, the both psi and psi square represents orbital. Okay, right. Then radial probability, the radial probability, that is the infinite small volume around the nucleus where the density of the electron wave is maximum, or the probability of electron is maximum, that is called radial probability. The infinite small radial volume around the nucleus where the probability of finding electron is maximum is called radial probability or density function, D function. Okay, that is mathematically represented as 4 pi r square dr psi square. 4 pi r square dr psi square. It is represented like this. Okay, important point. Directly you can expect that question in the examination. Okay, it appears several examinations so far. Right. That is radial probability. Next, the graph plotted between radial probability versus the radial distance from the nucleus is called, the graph is called radial probability distribution curve. radial probability distribution curves. Okay, now the radial probability distribution curves, okay, that is a graphs, that is concerned with the graphs. Next, another important concept is number of radial nodes, number of radial nodes, or radial node, or it is also called number of nodes, or you can also call it as number of nodal surfaces, or you can also call it as number of spherical nodes. Radial nodes or spherical nodes, remember, is equal to n minus L minus 1. Okay, important concepts, all these you should remember and practice, that is important. Okay, next one, number of angular nodes, number of angular nodes of an orbital. Angular nodes, or it is also called nodal plane, nodal plane. Okay, that is equal to always L value, that is always equal to L value for any orbital. Okay, that is always equal to L value, right? Number of radial nodes or spherical nodes, that is equal to n minus L minus 1, and the number of angular nodes or nodal planes equal to L value, right? Next, total number of nodes equal to, okay, total number of nodes equal to n minus 1. Remember, total number of nodes, total number of nodes equal to n minus 1, total number of nodes equal to n minus 1. You should remember these fundamentals, they are all, okay, total number of nodes equal to n minus 1. Okay, these points we can understand from the graphs. Okay, then quantum numbers. The principal quantum number signifies to explain size and energy. That means as the n value increases, size increases and the energy of that subshell or whatever that suborbitals present in that, there also increases. For example, see, in third orbit n is equals to 3. N is equals to 3 means K, L, M shell, that is nothing but M shell. Okay, in M shell, what are the possible subshells we have? Possible subshells are L is equals to 3, it should be 3 because the number of subshells equal to n value. So that means 0, 1, 2 subshells are possible. That means S, P, D subshells are possible. Okay, now we have, okay, so like this, so 3 subshells are possible. Now let us take P subshell. Okay, it is 3P subshell, right? 3D subshell, it is 3S subshell, right? Now let us take 2P, 3P and 4P. So, sorry, 4P subshell. Okay, 3P, 2P, 3P and 4P subshell. That means L is equals to 1. That subshell is L is equals to 1. It is belongs to second orbit, third orbit and fourth orbit. Okay, so now all the 3 subshells only, P subshells only. Now as the principal quantum number, as n value increases, energy increases. That means the energy of 2p orbital is less than 3p orbital energy, less than 4p orbital. You should remember that. Okay, for example, you take another one, s orbitals. S orbitals. Take the s orbitals. See, that is, for example, 1s, 2s and 3s. As n value increases, energy also increases. The energy of 1s orbital less than 2s, energy of 2s less than 3s, like that. So that is energy. Okay, size, energy of 1s smaller than energy of 2s, smaller than energy of 3s, like that. So that means as the principal quantum number increases, as n value increases, size increases, energy also increases. Okay, that we understand from the principal quantum number. Azimuthal quantum number. Azimuthal quantum number, it explains existing of elliptical suborbits in addition to the circular suborbits, that we explain. So in every given orbit, maximum one circular suborbit is existed, the remaining all are elliptical suborbits. Yes. Azimuthal quantum number is given by the symbol L. The value of L always equal to n minus 1. L is equals to n minus 1. Okay. L values are always equal to n minus 1. That means they are from 0, 1, 2, 3, so on. Okay, like that. That means always less than n minus 1. That is, it should not be equal to n. It must be less than n values. Okay. Next, azimuthal quantum number L represents subshells. It represents subshells. What are the subshells? The subshell values are less than, that is n minus 1. These values starts from 0, 1, 2, 3 and so on. Okay. These values represents an individual subshell. That is when L is equals to 0, that is S subshell. L is equals to 1, that is P subshell. L is equals to 2, that is D subshell. L is equals to 3, that is F subshell. Okay. These are all subshells. Okay. These are all subshells. Subshells. That means azimuthal quantum number signifies to explain existing of subshell and their shapes. Existing of subshells and their shape. That is, S subshell spherical, P subshell, that is P orbital is dumbbell, D orbital is double dumbbell, and F orbital is highly complicated structure. Okay. So that explains azimuthal quantum number signifies to explain existing of subshells and their shape. That is the significance of azimuthal quantum number. Next, magnetic quantum number. See, one more point in this azimuthal quantum number. How many subshells are existed in a given orbit? How many subshells are existed in the given energy level? That is equal to n value. For example, in first orbit, how many subshells could exist? Only one. Second orbit, 2 subshells. Third orbit, 3 subshells. Fourth orbit, 4 subshells. Okay. So, that points are important. You should remember them. That is, simply listening and forgetting means that is no use. Next one, magnetic quantum number. Magnetic quantum number discovered by Landé to explain the splitting of spectral lines under the influence of magnetic field, that is Zeeman effect, and to explain the splitting of spectral lines under the influence of electric field, that is Stark effect. To explain Zeeman spectral lines and Stark spectral lines, he discovered a new quantum number that is called magnetic quantum number. Okay, this magnetic quantum number signifies to explain orientation of suborbits, that means subshell. Okay, so the values of M depends on azimuthal quantum number value. M values depends on L value. The M values, that means the orientation values, each orientation value represents an orbital. Okay, these orientation values are ranging from minus L to plus L including 0. The total number of orientations are equal to 2L plus 1. Everything we explained. Okay, just I am taking the revision of the past. Okay, so the total number of orientations means the number of orbitals in the subshell. Number of orbitals in the subshell, that is equal to 2L plus 1. Okay, that is the total number of orbitals in the subshell. M values are equal to 2L plus 1. Okay, for example, suppose if it is L value, right? What does it indicate? What? Number of orbitals in the subshell. Number of orbitals in the subshell. Okay, so for example, 2p orbital, yes. So p orbital, number of orbital, that is M values for this 2p orbital. M is equals to 2L plus 1, 2 into 1 plus 1, that is equals to 3. Because for 2p orbital, p subshell, there is L value is 1. So 2L plus 1, that is equals to 3. That means p subshell contains 3p orbitals. That means this represents the number of orbitals in the subshell. Take one more example. d subshell. So what is how many orbitals are existed? M is equals to 2 into L. L value for d subshell is 2 plus 1, that is equals to 5. That means any d subshell contains 5 d orbitals. That means this represents the existing of maximum number of orbitals in the subshell. Okay, that is magnetic quantum number. Magnetic quantum number signifies to explain orientation of suborbit in the space. Okay, that is magnetic quantum number. Now another point. To represent an orbital in the atom, to represent an orbital in the atom, 3 quantum numbers are required. To represent an orbital in the atom, 3 quantum numbers are required. For example, see, lithium atomic number 3. Okay, lithium atomic number 3, 1s2, 2s1. This orbital I wanted to represent, not electron orbital I wanted to represent. Yes, that means to represent this orbital, or you can say p orbital. So this subshell is present in second orbit, that means n is required, that is principal quantum number. That subshell L value is 0 for s orbital, so that is subshell. In that subshell we have different orbitals are present. So to represent an orbital, orbital m, subshell L, shell n. Okay, so to designate an orbital, 3 quantum numbers are significant: principal quantum number, azimuthal quantum number, and magnetic quantum number. Okay, that is all important points. You have to analyze the concept, then only you can answer it. Okay, what about spin quantum number? Yes, simple, very simple it is. Spin quantum number represents the direction of spin of the electron. That indicates only the direction of spin. It's not going to connect with orbital or subshell or orbit. Okay, and another important point, spin quantum number is not derived from the Schrodinger wave equation. Earlier also in the session we explained that clearly, right? Okay, that is about quantum numbers, significance of all 4 quantum numbers. Next, coming to the orbitals, that is shapes of different orbitals. What is the shape of the s orbital, p orbital, d orbital, f orbital, and like that? Okay, what is an orbital basically? Once again, 95% probability of finding electron around the nucleus. Remember that percentage, that also you can expect as a question. What is the percentage of probability of finding electron around the nucleus to represent an orbital? That is, they will give different percentages like 20%, 40%, 60% and 70%. So that is 95% probability. Okay, orbital, that is 95% probability of finding electron, right? That space around the nucleus is called orbital. Yes. Next we have s orbital. S orbital is spherically symmetrical. S orbital is spherically symmetrical in shape. S orbital is spherically symmetrical. Okay, right. P orbital is dumbbell shape. Okay, dumbbell shape having 2 lobes and 1 nodal plane. Okay, now d orbital is double dumbbell, we know that. See here, one interested question I will explain you. Okay, now write down the question. I will give the question slow manner. Okay, note down that the radii of maximum probability, for 3s, 3p and 3d electrons are in the order. You got my question? Once again, the radii of maximum probability, for 3s, 3p and 3d electrons are in the order. I repeat again, the radii of maximum probability for 3s, 3p and 3d electrons are in the order. Okay, that is the question. Okay, that means you have different options like, so that is 3s greater than 3p greater than 3d, like that different options will be there. The hint for this you have to write. That is the point, you have to remember that. Based on the hint you can answer that question. Okay, so it is very simple and interesting also. Now write down that hint also. Radii of maximum probability of electron, radii of maximum probability of electron is less, that means E is smaller. For orbital having higher value of L, higher the value of L, radii of maximum probability is smaller. Okay, that means let us take examples. What is the example I said? 3s, 3p and 3d orbital. So for which, so here L is equals to 0, L is equals to 1 and here L is equals to 2. Okay, higher the value of L, so that is the smaller the value of radii of maximum probability. Okay, radii of maximum probability is smaller for the orbital having higher the value of L. Higher L value, lesser the L value, lesser the radii of maximum probability. Okay, therefore, so higher the value of L, lesser the radii of maximum probability. Okay, that means, so the radii of maximum probability for 3s orbital is greater because of smaller L value. It is greater than 3p, it is greater than 3d orbital. So higher the value of L, lesser will be the radii of maximum probability. That is the point you have to remember. Okay, important and interesting question. Yes, right. Now let me ask you one more question also. Yes, the question, okay. It is from our all force material only. The question is like this. Psi 321, the orbital with psi 321 or the electron psi 321. The wave function of an electron is 321. That is perfect. Okay, 321. Identify sum of orbital angular momentum, identify orbital angular momentum, angular nodes and spherical nodes. Spherical nodes of the orbital. Okay, so that is for an orbital. So psi 321, find out the sum of orbital angular momentum. Okay, then angular nodes and spherical nodes we have to identify. So the options we can give like this. First option, say for example, root 6h plus 2 pi by 2 pi. Second option, root 6h plus 8 pi by 2 pi. Third option, root 6h plus 4 pi by 2 pi. And last, fourth option, root 6h plus 3 pi by 2 pi. So these are the four options we can give. Now find out first orbital angular momentum. See what is the meaning of this. Psi 321 means n is equals to principal quantum number value is 3 and azimuthal quantum number value L is equals to 2 and magnetic quantum number value m is equals to 1. That is the representation of that orbital. Okay, so the representation of the orbital, n is equals to 3, L is equals to 2 and m is equals to 1. That is the designation of that particular orbital. Okay, right. Now angular momentum is equals to under root 6, that is L into L plus 1 h by 2 pi h by 2 pi. That is equals to under root. L is equals to what? What is the L value of that particular given orbital? L value is 3. So L value is 2. So azimuthal quantum number given L is equals to 2. So that means 2 into 2 plus 1. That is 2 plus 1 3. 3 to the 6. That is equals to. So it is yes h by 2 pi. H by 2 pi. That is equals to root 6h by 2 pi. That is angular momentum, orbital angular momentum, right? Next one is number of angular nodes. Number of angular nodes always equal to L value. It is equal to L value. That means number of angular nodes equal to L value. So that is number of angular nodes. Number of angular nodes is equals to L value. That means it is equal to, what is the L value for this? 2. Yes sir, it is 2. Yes. Plus number of spherical nodes. Number of spherical nodes is equals to n minus L minus 1. Yes. N value is 3. 3 minus L value 2 minus 1. That is equals to 0. Yes. So therefore it is equal to 0. Forget about it. So now that is equals to, this is equals to, that is sum of the orbital angular momentum. Next angular nodes and spherical nodes. Spherical nodes equal to 0. In this you got. So now it is 6h under root 6h by 2 pi plus 2. That is equals to 6h plus 4 pi by 2 pi. That is the right option. Okay. So like that you have to understand the given concept of the question. Okay, that is psi 321. Okay, for this orbital, calculate sum of orbital angular momentum, angular nodes and spherical nodes. Okay, instead of that angular nodes you can also understand, so it is yes, radial nodes. It is also nothing but radial nodes or spherical nodes. That is very important question. Okay. Next, this is one type of question. Next, let us understand another different questions from the orbitals. Okay. Yes, the next question is based on the quantum numbers. Based on the quantum numbers. Maximum number of subshells present in an orbit. How many subshells are present in an orbit? That is equal to always n value. Okay, just now we explained the significance of all the quantum numbers. Okay. Next, based on the orbitals, the subshell with L is equals to 1. What is the shape of that orbital? The subshell with L is equals to 1. That is nothing but a p orbital. That is nothing but a p orbital. The shape of the p orbital is a dumbbell. Okay. Similarly, when L is equals to 2, that is nothing but a d orbital. The shape of the d orbital is double dumbbell. Okay. That is double dumbbell. Right. So now we have discussed about that is Schrodinger wave equation, significance of the 4 quantum numbers, and we explained, that is, we have some information about the shapes of the orbitals. Now let us understand another one. Okay. Next question is, how many radial nodes are present in 4D orbital? Number of radial nodes for 4D orbital. Number of radial nodes for 4D orbital. Radial nodes. Number of radial nodes. That is one question. Similarly, number of angular nodes for 4D orbital. Angular nodes. Angular nodes. So 2 questions I am asking from the same. For 4D orbital, or you can say for 4D electrons, how many radial nodes and how many angular nodes are present for that? Okay. So the number of radial nodes always equal to n minus L minus n minus L minus 1. You should remember this. That is n minus 4D orbital. N is equals to 4 minus L value 2 minus 1. That is equals to, okay, 4 minus 2, 2, 2 minus 1, 1. And angular nodes, number of angular nodes equal to L value. Number of angular nodes equal to L value. That means For any d subshell, L value is always 2. Yes, angular nodes are 2 and radial nodes are 1. Okay, like that we can answer. Next one more question based on the similar concept. What 3s orbital? For 3s orbital, number of angular nodes. For 3s orbital, number of angular nodes. For 4s orbital, number of angular nodes. Only number of angular nodes I am asking. Only number of angular nodes. For 3s and 4s orbital. So number of angular nodes always equal to L value. For any s orbital, L value is 0. Therefore, okay, for 3s orbital, number of angular nodes 0. And for 4s orbital, number of angular nodes again 0, because L value is equal to 0. Like that we can answer the questions. Okay. Next. See, the subshell with L is equals to 1. The subshell with L is equals to 1. Okay. The subshell with L is equals to 1. And the orientation value is 0. The orientation value is 0. The subshell with L is equals to 1 and its orientation value is 0. What is the designation of that orbital? What is the designation of that orbital? So that means when L is equals to 1 means it is nothing but P subshell. P subshell has 3 orientation values, that is equals to -1, 0 and +1. We know that. Okay. And these are the 3 p orbitals. Yes, what are the designations of 3 p orbitals? Px, py and pz orbitals. So remember, conventionally the orientation value for pz orbital is 0. Okay, that point we should not forget. Okay, for conventionally the orientation value for pz orbital is 0. That means orientation value 0, that is nothing but pz orbital. Okay, like that we can answer. Okay, this is about some important revision points based on your Schrodinger wave equation and quantum numbers and shapes of the orbitals. In the next session we are going to discuss about electron configuration.